All right, we need to go ahead and get started. We've got a lot to do today. Let me get over here. I do have your quizzes from last time. I did put the grades in Canvas. All right, so let's get started. Any questions on the homework? Homework?
Number 19?
Oh, I'm expecting a phone call. You know how when you get something delivered to your house, they give you like a window and then they give you a heads up that they're coming? So I'm expecting that call. So if my phone rings, I'm going to take it outside real quick, okay? Okay, which problem?
That's 19.
Number 19? Well, let me take a look. Okay, number 19. Is that what I'm hearing?
That's what I said.
What else? What else?
27.
27 and... That it? Okay, I'll start with 19. 2/3 x to the 2/3. So you're given that f double prime of x is 2/3 x to the 2/3.
Yes, sir.
And you're asked to find f. Right? Little f. But you're given little f double prime, right? So we're going to find little f. So that means we have to go backwards once to find f prime and then backwards again to find f. So our first antiderivative will get us from f double prime to f prime. So I bring the 2/3 down and then I'll have x. I'm going to raise it to a power, but I'm going to add 1 to that. So 2/3 plus 1 is 5/3. And then I put 1 over 5/3 in front, which is the same as 3/5. That's multiplication. So then I cancel the 3's. I have 2/5 x to the, plus c, x to the 5/3 plus c. Right? Okay, so now I'm just going to go again. Right? This is my first derivative, and I don't know what c is. I'm given no information about c, so I'm just going to leave it as c. And so now I go to little f. It's the antiderivative of this. So the antiderivative of this one here, I'm bringing the 2/5 down again. I'm going to leave myself some space in front of it. Here's x. I'm going to add 1 to this again. 5/3 plus 1, 8/3. And then 1 over 8/3 here is the same as 3/8. That's multiplication. Plus, now the antiderivative of c is cx. And then we have another constant of integration, which I'll call d. And then just resolve the number out here. This is what? 1, 4. So what? 3/20. So you have 3/20 x to the 8/3 plus cx plus d. That's it. That's number 19. Number 27. you're given that f prime of x equals 2 cosine t, oh, sorry, it's t. 2 cosine t plus secant squared t. And they give you some restrictions on t, which we really don't need. That's just to make sure that we're within certain bounds so that we don't get something undefined. And then they give you that f of pi over 3 is 4. Right? And you're asked to find little f. So find little f. This time we only have to go backwards once because we're given f prime. So little f of t, we need to bring this constant down because it's attached to the front of cosine. And then we ask ourselves, what is the antiderivative of cosine t, which would be sine t. And then here we ask ourselves, what's the antiderivative of secant squared t, tangent t, and then plus some constant. Now we use this information to actually nail down what c is. So using the fact that f of pi over 3 is 4, that implies to us that when we plug pi over 3 into this expression, 2 sine pi over 3 plus tangent pi over 3 plus some constant, we should get 4 to come out. So we just need to know what these values are. So going to your unit circle, sine of pi over 3 is what? Sine root 3 over 2. It's the y coordinate on your unit circle. You're at pi over 3, which is up here. Sine is the y coordinate. Right? Remember, this is 1/2 root 3 over 2. So sine of pi over 3 is root 3 over 2. Are y'all okay with that? Yes? And then plus, yeah, the 2's will cancel. Tangent of pi over 3 is the y coordinate divided by the x coordinate. So root 3 over 2 divided by 1/2. 2's go away, you just get root 3. And then when we have plus c equals 4. So cancel these 2's. And now what you have is, what, root 3 plus root 3 is 2 root 3's plus c must be 4. And solving for c, you get c must be 4 minus 2 root 3, whatever that number is. But this is our constant now, so we can actually come back into this function right here where we have found little f, replace c with this number, and we have f. So the final answer is this line with 4, ooh, it's dead. Uh-oh. Thought I had another color here. Let me try this one here. They're all over the room. It's just a question of do they work. 4 minus 2 root 3. And then box that up, that's your answer.
What number was that?
That was number 27. Okay, let's get moving. If you have any other questions, let me know. But not right now. Sorry. How are y'all doing today? Y'all okay? Feels, yeah, I'm dragging right now. I don't know. This whole thing where my Tuesdays and Thursdays, I'm getting into my office like around 8:45, and I don't have anything until this class, and I'm just like, oh. You know, I'm watching YouTube videos and on math-related stuff, of course, but, you know, it's just still, man, it's a drag. I need to give more quizzes or something, that way I have something to grade. Okay, we're going to move to 5.5. all right? We're going to probably knock this out, hopefully pretty quick, so that we can get into the next section, which will be, we're going to skip from there, I believe, to 6.1. Is that right? Yeah. So let's see how we do with this. So 5.5 in the notes, substitution rule. So first, some notation. You know, we were saying before, you know, that we had this little f, and then we had this concept of finding its antiderivative, right? I'm just going to put anti, right? And we called it capital F. And so every time I wanted to tell you find the antiderivative, I would have to tell you find the antiderivative, right? But we have a different notation that we use that actually tells you find the antiderivative, and it's what's called the integral. So if we're given a function little f of x, if we wish to find the general antiderivative, then we write the following. So it's this symbol, okay? And then we write the function here, and then we tack on to the end of it, and it's like multiplication, this thing dx, all right? So let me go through what each of these things are. First of all, the entire thing, all right, is called the indefinite integral, right? The whole thing together is called the indefinite integral. This symbol here is called the integral sign, and it's actually an elongated S because it actually is a summation, which we'll talk about, but it'll be much later. Like after we get through most of chapter 6, we'll actually figure out why it's a sum. And then f of x, which is the function we're trying to find the antiderivative of, is called the integrand. It's kind of related to, you know, if you had a radical, the thing underneath it was called the radicand. Here, when you're doing an antiderivative, there's an integral sign. It's called the integrand. The dx is called the differential. And the way I want you to look at it right now is that this just keeps track of what the independent variable is in the problem. So if this says dx here, that means that your integrand is, you're treating the x's like the variables, all right? We're not going to see anything other than that, but if you go on and do more calculus, you'll have functions in here that are functions of more than one variable. So this right here keeps track of what you're treating as the variable, all right? Okay, and then when you actually figure this out, you find the antiderivative, right? And we call that capital F of x. So that's called the antiderivative, right? And then the c that we add on the end is called the constant of integration. So this whole process of finding antiderivatives, okay, the whole process of finding antiderivatives is called integration. So in Cal 1, we did the process of finding derivatives. We called it differentiation. And now in Cal 2, when we're going backwards, we call it integration. And that again ties into the idea of this being called integral calculus. Cal 1 is differential calculus. This is integral calculus. All right, so some things we've already seen. We saw the power rule last class. You used that on your homework. And we said that this power rule takes care of all powers of x. And there was that one special case where n was -1 where it became the natural log. But that formula we should have. In addition to that, on your formula sheets, on page 6, reference page 6, is a list of 29 integrals. And so all of these use the notation that we are learning here today. So for example, I'm going to just look at one of these here. Formula number, let's say formula number 7 says this. It says that that's equal to what? Sine u plus c. So the integrand, the function we're trying to integrate, find the antiderivative of, is cosine of u. So we're using u instead of x, all right? And the differential tells us, yes, u is the variable, right? So the antiderivative of cosine is sine plus some constant, right? Now this table gives you a bunch of formulas, and you need to become familiar with at least the first 20, all right? You should be, I'm not saying you need to memorize them. I'm just saying that you need to know that they're here. for example, if you have something like this, integral of 1 over 4 minus x squared dx. Okay, and when you see that, you're like, well, I'm not quite sure how I'm going to do this, but wait a minute, hold on. Looks like formula, which one? Look at 19. 19 says du over a squared minus u squared, right? That's it. So that formula is the same as this. The du is like multiplication. It can be slid out to the side like that. And then the a here in the problem, what do we say the variable is here? U, because the differential tells us that. So we're going to treat the a as a constant. So for our formula over here, what we're trying to do, using 19, we can see that a for us would be what? 2, right? 4 is 2 squared. So that right there falls into this formula pretty nice, doesn't it? And so what is the answer? We don't have to do any work. What is the answer? 1 over 2 times a. Now remember here, that's a squared is 4, so a must be 2, right? So 2 times 2, that's our a, and then natural log of the absolute value of u. What's u for us? U is actually x. Then plus 2, then x minus 2, and then close it, and then plus some constant. All right? So it'd be 1/4 the natural log x plus 2 over x minus 2. That's it. We'd box it. We'd be done. So please be aware that there are a lot of things on here you've seen, like mostly 1 through 10 are all probably things you've pretty much seen. But the ones on the right, 11 through 20, some of those aren't as obvious, or things that you didn't get in calculus 1. So just be aware of that. Now, if you have a book, these formulas, if nobody tore out your formula sheets, if your book still has formula sheets in it, I stopped at the second page 6 of the formulas, but there's actually page 7, page 8, page 9, page 10. There's actually 120 formulas in this book for finding antiderivatives. And I've seen books as thick as this book full of formulas for antiderivatives. I mean, there's a bunch out there, right? A lot of times when you get to like a physics class or something like that, there's integrals that come up all the time. And so instead of having to figure out how to find the antiderivative, they usually have a formula for it already, so you don't have to do it. Just sharing that with you. But we're going to try and do a bunch of integration without needing the 120 that are in the book. We're going to do a lot of it just by different procedures. Okay, any questions? No? All right, next thing. Substitution. All right, so let's talk a little bit about substitution. Right now, the only way we can find an antiderivative, right? The only technique we really have is that we have to hope it's a power of x, right? Or we have to hope it's something we saw in Cal 1, like secant squared. The antiderivative we knew was tangent, right? Tangent derivative is secant squared. So that's all we've got right now. This rule, substitution rule, is really our first kind of technique, our first tool in our toolbox of trying to find antiderivatives. And it's the most basic one, but you can't do anything past this if you don't get this rule down. Okay, so everything builds off of something like this. So we'll start with, let's just take a look at Cal 1 problem, which would be finding the derivative of that. So if we find the derivative of this, let's see who's awake today. I'm going to call on Paul. But I know you're writing things down, Paul. I'm just trying to wake myself up, so I just figured we'd talk. Okay, so cosine of what? X squared times 2x. Okay, that's it. So chain rule, right? And of course you could reorder it. Sometimes we like to put those numbers in the variable out front, and we're done. That's it. That's Cal 1. Now, think about this the other way around. Okay, so let's say we start there. And I'm actually, see in my example there, I want us to look at, forget the 2's there. Let's just look at this problem right there. Okay, so forget the 2. The 2's not there. I mean, it's here, right? But this is a separate problem. So the issue we have here is that there's multiplication here, right? There's our multiplication. And we talked last class that antiderivatives, when you have products, is not easy, right? It's not simple. You can't just find the antiderivative of each one. So how are we going to go backwards from this to this, right? I mean, how are you going to do it? Are you just going to look at it and go, sure, that's the derivative of 1/2 sine x squared. Because, oh yeah, that 2's not there, and I know that the 2 would come out in chain rule. Are you going to be able to see that far ahead? You understand what I'm saying? That can be somewhat challenging, right? So there's got to be some process that allows us to go backwards with more efficiency. And that's what substitution rule is. So let me show you what the strategy is. I have it in 6 steps. What we're going to do is we're going to look at the integrand. The integrand is the entire thing here, right? I'm going to look in there and I'm going to try and find something, okay? Something in here. And also within here, the derivative of that something is sitting in here. And then on part 4 it says the derivative that you see might be off by a constant, and that's okay. All right, so what do I mean by that? I mean, look around in here. Oh, that's the call. Let me turn this off real quick. Y'all look. Okay, let me make sure. Did y'all get it? I thought someone was going to come up here and write it down. Okay, so we're looking for something and its derivative. We're okay to be off by a constant, right? That's where we are. So you see x squared? What is the derivative of x squared? 2x. You see an x? So that's the something, and that's its derivative. We're off by 2, right? So what we're going to do now is we let the u be something. So this is where we're going to make a substitution in the problem. I'm just going to walk here on the side. I'm going to say, look, let u be x squared, right? That means everywhere I see an x squared, I replace it with a u. Now, the next step is to take the derivative on both sides of this equation implicitly with respect to x. So what's the derivative of u with respect to x? Du dx. And then what's the derivative of x squared? 2x. Right? And then derivative of x with respect to x would be 1. So this is it, right? Everyone with me? Okay, now the next thing I'm going to do, and this is going to be pretty much standard the way I'll do it the rest of the semester, is I'm always going to clear this dx on this side, basically multiplying both sides by dx. So getting du is equal to 2x dx, right? And remember, that's multiplication right there. So I look over here, and I said I saw something in its derivative. I'm just going to rearrange it a little bit so that perhaps it looks a little easier to work with. I won't always rearrange it as we move on. I'm going to put the cosine x squared here. I'm going to slide the x that's back there right here and just push it right in between those. X dx. Remember, that's multiplied, right? So I have an x dx in the problem, right? I have x dx here. And over here, I have an equation that actually has x dx in it also, right here. The thing I don't have is the 2, right? So I don't want this 2 here. So what I'm going to do on this equation is I'm going to multiply both sides by 1/2 or divide both sides by 2, however you want to look at it. I like to put it as a number out in front. So 1/2 du equals x dx. And so once I've got this matching up exactly with what's up here, what I'm going to do is actually make the substitution now. I'm going to rewrite the integral, and everywhere I see a u, I will replace it with x squared. Everywhere I see an x dx, I will replace it with 1/2 du. So let's do it. Now I'm using an arrow here to let you know that I am rewriting the integral, but my variable has changed, so I'm not quite saying they're equal. I'm just saying this is being transformed into some new integral. Here's what it is. What? Cosine of u, so cosine u, times, and then the x dx we said was 1/2 du. And at this point, I can take that 1/2 and I can actually slide the 1/2 in front of the cosine and then actually out in front here, because remember, with antiderivatives, the constant, if they're attached to a function, it's just going to come with us. So I'm just going to put here, this one equals 1/2 times, so there is multiplication there, cosine u du. That's all we'd have left. And this, because we've changed the problem, the variable in the problem, we actually know what the antiderivative of cosine u is, right? It's sine u. So this becomes no more integral sign, right? Watch. No more integral sign, 1/2's coming for the ride. The answer is sine u, right, plus a c. So when you actually find the antiderivative, two things happened here. The integral sign went away, right? And the du just kind of disappears. And that's because the du is only keeping track of the variable. Yes? Question? No? No? So some people like to say, like, the integral sign goes away and the du somehow becomes the constant or something. So you don't sit there and go, where'd it go? It's the constant. That's not really what it is, but let's just, if that helps you, remember the constant. All right, so this is our answer, but we're not done because our original problem was in terms of what variable? X, right? So I need this to go back to x. But I know what u is. U is x squared. So now on the last line, and this will be my final answer, is that this equals 1/2 sine u, but u is x squared plus c. And that's it. And we could check that ourselves to see that that's correct by doing what? Taking the derivative, right? So if we took the derivative of this, you would get back this. All right, so the key is to look for something, right? You're trying to find something in its derivative and then make a substitution and hope for the best, right? That's what it says. Make the substitution and go for it. See what happens. And that's it. That's substitution rule. Have a good day. We should probably do some examples, right? Okay, let's try some. All right. Find the antiderivative of x squared square root x cubed plus 30 dx. Use the substitution u is equal to x cubed plus 30. So in this problem, I'm actually going to lead you to the answer. I'm going to tell you what the substitution should be. All right, so I'm telling you what your u should be here, but let's see why that is the choice of u. You have this integral, right? Could you use the power rule from last class? Is that even possible here? Because there's multiplication, you can't just do this and this, right? You can't split this into two because there's some in there. So there's no way you could use any of the rules from last class. It's definitely not the derivative of something you learned in Cal 1 that was like a simple formula, like cosine, right? So this is something that's going to require a little bit more. So now we go to this technique. We look for something and its derivative, and we hope that we're off by a constant at most. So we look underneath the radical, and we see we have a cubic function, right? A cubic expression. And we know that the derivative of a cubic expression would be quadratic. In fact, the derivative of x cubed plus 30 is what? 3x squared. So I have an x squared. I'm off by 3. That's okay. I at least have the x squared, don't I? Now, why not choose for u instead of this? Why not use this? Why not take the whole thing with the root? What would the derivative of this be? It'd be 1 over 2 roots of x squared plus 30 times 2x, right? And the 2's would cancel. Now, what we said for substitution is that you want to see something and its derivative. So if I chose this, do you see that there? Yes, there it is. Do you see its derivative there? Do you see a square root of all this junk in the denominator up there? No, right? So this would actually be too much. You actually picked too much of a u for this to work out. Does that make sense? So you're trying to find this balance, picking enough to make it work, not too much and not too little. What would be too little? This is a good one here. How about if I just say u is x? Because look, what's the derivative of x? 1. Do you see a 1 there? Of course there's a 1 there, right? But if you actually make this substitution, what will happen is every x gets replaced with a u, and the dx gets replaced with du. And what you have is the whole problem rewritten exactly the same with u's instead of x's. So this would be not quite enough of a u to choose. This would be too much, and that's perfect. Yes?
Why did you just pick x cubed?
X cubed. Oh, why didn't y'all tell me this should have been cubed? Why didn't y'all tell me that? Cubed, right? Cubed, and this would have been 3x squared. That wouldn't have canceled. I'm sorry. Right? Okay, I should have caught that earlier. In any event, this didn't work anyway. right? So what about just x cubed, right? That would actually work too, okay? But what'll happen, see, I don't want to foresee this too much, but I'll try. If you pick this to be your u, right? Then in your new integral, this x squared in dx should be part of your du. It should be out here somewhere. But you're still going to have the square root of what? U plus 30, right? Do you know the antiderivative of the square root of u plus 30? Not right off the hand. But if the whole thing gets replaced with u, then it's just the square root of u, and the antiderivative square root of u we can use the power rule on. So you might have to learn that lesson by doing some and seeing that it takes you a little longer if you don't pick quite enough. All right, so let's use this substitution, right? Here we go. So what is du? What is the derivative there? So du dx is 3x squared, right? And then that means that du is 3x squared dx. Do you have a 3x squared dx over there? Not quite, right? You have square root x cubed plus 30 times x squared dx, right? You have the x squared dx. So let's go ahead and try and isolate this x squared dx here on this equation. So do what? Multiply both sides by 1/3. And so what I'll do is I will replace this x squared dx with 1/3 du, and I'll replace the x cubed plus 30 with u. Are there any questions? You'll see this happening? All right, so let's see here. Yo. That's your name, right? Did someone mess with you? Or did you put that? You put that?
I put yo. Whatever.
Okay. All right, yo. All right, yo.
Yo.
So, yo. Oops, I'm trying to silence this now. What is that integral going to turn into? Yo. What am I replacing x cubed plus 30 with?
You're gonna replace it with the du?
Yes. What is x squared dx being replaced with?
So you're replaced with the
1/3 du, right? 1/3 du. Does anybody have questions on that? Okay, so now what I'll do is I will clean it up. I'm going to take that 1/3 out to the front. And the square root of u, Chris, is going to, should I leave it as square root of u if I'm going to take the antiderivative? What should I write it as?
x squared plus 30.
Not yet. We haven't done the antiderivative yet. But if I want the antiderivative of the square root of this, do the 1/2, right? So change it to u to the 1/2 first, and then du. And now this is a power rule, right? Your variable's u now. It's a power rule, so I have the 1/3 out front, and then I'm actually taking the antiderivative now, so the integral sign is going to go away. I'm going to write u, and let's see, Kelly. I couldn't see your name tag there. I know you were trying to look over the camera there, so I'm calling on you to get you going here. Antiderivative u to the 1/2. U to the 3/2, 2/3 in front. And
plus c.
there you go. So remember the du afterwards, you can look at it as becoming the plus c, so you don't forget about it. Because everyone always asks, what happened to the du? It's just keeping track of the variable, but if you want it to do something, then let it be your c or something. All right, so this becomes, let's see, 2/9 u to the 3 halves, right? Plus c, and then we can actually go back now and replace u with what u was. So what was u? X cubed plus 30. The entire quantity, though, raised to the 3 halves plus c. And that's our answer. And we could always check it by taking the derivative, couldn't we? I have this vivid memory from my childhood when I was about 9 years old. My grandfather had a V8 engine up on an engine stand in his shop, and he had it all hooked up, and he had it running, and it was really loud, and I had little earphones on, and he had me holding a camcorder, like the old ones with the VH tapes that would go in them, and he had me holding it while he was demonstrating. He had come up with variable valve timing for an engine, and he was doing it years before it came out, and he was just doing it and showing me, and I didn't have any idea what it was, but I was recording. So after that, you know, I'm in there, and it's like, you know, it smells like exhaust in there, and he's doing something on paper, and he's asking me, like, okay, I have 3/5, and I need to subtract from that like 1/7, and he's doing some arithmetic like that, fraction stuff. And I had no idea how to do it. I was so terrified. Like, I sucked really bad at fractions for a long, long, long time. You know, so I just remember just feeling terrified that this old man could do all this fraction stuff in his head, but I couldn't do it at all. Like, I couldn't do it. And it took me, you know, till about calculus to really get good at it. So I guess when I'm calling on you, I'm expecting you to add 1 to 1/2. I know for some of you might be sitting there going, I hope he doesn't call on me and ask me to add 1 to 5/7, you know, but you want to get comfortable with that because you don't want that slowing you down, all right? Get good with those fractions, get quick with them. All right, shall we do another? Yeah, of course. Of course we should. All right, this one, I'm not going to tell you what the substitution should be. Hold on. This one's tricky. So, I don't think this falls into the category of just basic power rule, right? This is not the derivative of something you know from Cal 1, because there's a lot going on in here, right? So you're looking for something in its derivative. Let me make sure I think I wrote that down wrong. Yes, that's a 4 down here, sorry. I was like, uh-oh, that's not going to be good. All right, any volunteers for a candidate for u? X to the 4th? Because you see its derivative? What's its derivative? 4x to the 3rd. Do you see x to the 3rd? Okay. That's why I put this problem up here, because that's not correct. That's not going to work. Now, let's pay attention to why. You do have x to the 4th, but you actually have 1 over x to the 4th. You don't have, I mean, there is an x to the 4th down here, but if you slid this out here, it's actually 1 over x to the 4th, yes? And more importantly, the derivative of x to the 4th is trapped inside of a function. There are two things that you really don't want to have happen when you pick your u. You don't want the derivative of that u to be trapped by anything. You don't want it to be stuck inside of the argument of a function. You don't want for it to be in a denominator. You don't want it to be under a square root. You want that derivative to be by itself, just a factor that you can factor out. Because remember, don't we get that du and put it over here and try and get it to go away and match it up with something? right? If it's stuck in here, how are you going to pull it out? And you won't be able to. So maybe something else. Yes? 1 over x to the third. That doesn't seem as natural, but that's the same as x to the negative 3, right? And the derivative of this is what? Negative 3 x to the negative 4, right? Which is the same as negative 3 times 1 over x to the 4th, isn't it? Do y'all see that? And didn't I just say x to the 4th? That is actually a 1 over x to the 4th. Zach, do you see that? Yeah? Okay. That looks like it's going to work. So let me just finish writing this one line. I have du is equal to negative 3 times 1 over x to the 4th dx. So all I did there is what I'm going to do every time, which is bring the dx over here. And so what I'm going to try and do is see if I can manipulate that expression up there to make it look something like this so I can do my replacement. So I'll rewrite the problem over here as secant squared times 1 over x cubed times 1 over x to the 4th dx. So all I'm doing is sliding that secant squared out here and leaving a 1 over x to the 4th and then the dx. Because it's all multiplication, it doesn't matter how I put those together. This right here is what I'm trying to get to match up. I have it right here. So again, I'm off by a constant, negative 3 is what I'm off by. So I'm going to divide both sides by negative 3 or multiply both sides by negative 1/3. I don't think I want to erase that. I'll write it down here. So this will be negative 1/3 du equals 1 over x to the 4th dx. And Ruben, how should I rewrite this, Ruben? Since I've got it all, I think I've got it all ready to go for you here. Okay, so integral sign, then what? Secant squared u times negative 1/3 du. That it? That's it. So we replace the 1 over x cubed with u. We replace the 1 over x to the 4th dx with negative 1/3 du. That's it. We can pull the negative 1/3 out of that completely and then hope that we know the antiderivative of secant squared of u. And you do, right? It's tangent u. So this becomes negative 1/3. You want me to go ahead and do it now? Or do you want me to rewrite the integral? You want antiderivative now? Yeah? Tangent u plus c. And then replace u with what it was. What was u? 1 over x cubed plus c. We're done. So we're starting to pick up a method that is having some success with some of these more complicated looking expressions, right? We have not checked any of these, have we? I mean, like we haven't checked any of the answers, but we could just take the derivatives. Okay, let's try another one. How about what the hell? I'm so sorry, everyone. I'm just going to make sure this is not them. Hello? Yes? It's a 9, actually. There you go. Is that better? It's a Q.
That's a key.
So while you're trying to figure out what U is here, the thing that's going to get really difficult with this is that, you know, we have the substitution is the first kind of approach to doing things. After we do this, we're going to do integration by parts. That'll be the next sort of technique. Then after that, we're going to have what are called trig integrals. Then we're going to have something called trigonometric substitution. And then we're going to have partial fraction decomposition. And so we're going to have this like big old toolbox full of things that we can use to try and find antiderivatives. And so when you're faced with a problem like on a test or like in another class, nobody is telling you this is done by substitution. That's the challenge, is for you to be so good at all the methods that you can just see what method you're going to need to use. And that takes a lot of practice to be able to see it ahead of time. All right? So we have to kind of keep ourselves grounded here. Even if you kind of get this, you have to understand that when everything starts to get piled onto this, all the other techniques, you almost forget about this technique, you know? And so you try something really hard when it was something very easy. Or maybe you make a problem that's really hard too easy. And I don't know if that makes sense. Okay. Anybody have a U for me? E to the x? So you see, where are you seeing an e to the x? I see two of them. I see an e to the x and an e to the 2x, right? So you're saying, which one are you treating as the u? Both or this one? Okay, if you treat this as e to the x, I'm going to write it down. U is e to the x. What is its derivative? Its derivative is e to the x dx. Now, this was really du dx, and I brought the x over. I'm going to stop doing du dx and just bring the dx over every time. All right, so if u is e to the x, its derivative is e to the x dx. I want to know where you saw its derivative then. I'm just going off. You said that you were treating this as the u? Because if that's u, then where's its derivative? It would be down in the denominator, wouldn't it? And I said we don't want the du, the derivative of it, to ever be in a denominator or under a root. We want it all by itself, don't we? That's what I said. So, I don't know. Should we stick with it? What do y'all think? Anyone want to keep this? Anyone want to try something different?
For you, I guess in parentheses 9 plus e to the 2x.
You want to try the whole thing? The whole thing?
Yeah.
So okay, so this is our second candidate for you. I'm not going to tell y'all which one's going to work yet. I'm just trying to get your train of thought here. E to the 2x. Okay, let's look at its derivative. Derivative of 9 is 0. What's derivative of e to the 2x? E to the 2x times 2 because of chain rule, right? Okay, so if that whole thing is u, do you see its derivative anywhere? I see e to the x dx. That can be slid out, can it? But I don't have e to the x dx. I have e to the 2x dx. Sean?
Can it be a 3 plus ex? U?
3 plus, you mean like 3 squared plus? I'm not sure what you mean by 3. Because of the 9?
Yeah, change that to 3 plus e, and that's squared.
Ah, okay, I see what you're saying.
Squared.
Like change it to 3 plus e and then squared, like this? I think that's what you're saying. But this is not this, because you would actually have to FOIL this out and you'd have,
Right?
oh yeah, e to the x, like this? Is that what you meant? I don't know, yes? Or did you want the x out here? Either way, if you squared this, it won't be this, because you'll have some middle terms. What's that? What do you got, Luke?
I was going to say 1 over what I said there. Yeah, 1 over 9 plus.
You want to go 1 over the whole thing as u? The derivative of that might be pretty ugly, though, right? If you let u be 1 over the whole thing, the derivative would require like some quotient rule and stuff to get that. You can't split it into two fractions, right? Because you have one numerator, two denominators. What's that?
Make u equal 2x.
If u is 2x, the derivative of 2x would be 2, and you're off by a constant, but that would almost be the same as doing x, just u is x. Okay, so look, the correct way is this way, but the problem is that this is not the u, this is the u, and you have to rewrite it first. So watch. Isn't that the same thing? Isn't e to the 2x e to the x squared? Isn't it? Because you just multiply these two together, 2 times x is 2x. Now, if this is your u, right? If this is your u, the derivative of e to the x would be what? E to the x dx, which you have right here. So that might work. Maybe what I can do is, I'm going to come down with this a little bit. I'm going to rewrite this as integral 1 over 9 plus e to the x squared times e to the x dx. So I'm sliding that e to the x to the outside so that you can really see it's sitting there. So what I'm going to be able to do is replace this right here with what? That's exactly what I have here, right? That will be replaced with du. I'm going to be able to replace the e to the x right here with what? U. And then let me just see what I have, all right? I'll look at it after that.